Picture this. You're hurtling down a narrow street doing about 45 miles an hour. Out of nowhere, a pedestrian steps right out into the street, completely blocking your path. You slam on the brakes, but physics is unforgiving. You just can't stop in time. If you swerve right, you're going to slam into a solid concrete wall at full speed. If you go straight, you hit the pedestrian. Now, imagine you aren't actually the one driving. Imagine a few lines of code are making that choice. What we're talking about here isn't just some hypothetical nightmare. It's a very real, incredibly pressing engineering dilemma. Welcome to this explainer, where we're going to be diving deep into the collision between autonomous technology and human ethics. Think of it as a modern, high-tech adaptation of the classic trolley problem. For decades, that was just something people debated in college philosophy classes, a totally abstract thought experiment. But today, the trolley problem is literally sitting on the desks of software engineers. When a self-driving vehicle is faced with an unavoidable crash, the algorithms running that multi-ton machine have to make a choice. They have to prioritize lives. But before we even get to how a car makes a life-or-death decision like that, we really need to understand how it even knows what's in front of it in the first place. To kind of ground this incredibly complex challenge, let's strip away all the fancy AI for a second. We're going to look at a charmingly simple student science experiment from our source materials. The student's hypothesis was beautifully straightforward. If we use cardboard or metal or concrete, then the car's speed will change. They essentially set up a toy car, put different obstacles in front of it, and just watched to see if the car's basic sensors could detect the difference and react. And honestly, this brilliantly captures the absolute foundational baseline of all autonomous driving, because before a car can even start debating ethics, it has to accurately and instantly answer one simple question. What exactly is right in front of me? Like, is it just an empty cardboard box blowing across the road? Or is that a solid concrete barrier? Figuring out the difference between those two things is the absolute biggest hurdle in autonomous engineering. So to answer that question today, modern vehicles have definitely graduated from those little toy sensors. Now they're using advanced 3D flash LiDAR. You've probably seen those older, clunky systems that physically spin around on top of a car's roof, right? Well, a 3D flash LiDAR is completely solid state, no moving parts whatsoever. It fires a single massive flash of laser light to capture the entire scene all at once. If you look at this depth map, those colors aren't actually real colors. They represent changes in recorded distances. The system reads all these little pixel clusters to instantly build a full three-dimensional model of the world around it. It's basically the car's visual cortex. But as you might guess, creating this kind of synthetic vision is staggeringly expensive. Our sources point out that a really sophisticated receiver for this exact kind of setup could run you up to $150,000. Yeah. So obviously some major advancements are going to be needed before this kind of tech becomes affordable for your everyday passenger car. But here's the kicker. Even if cost totally wasn't an issue, engineers are still bound by the strict laws of physics. There's this really delicate, uncompromising trade-off between focal length, field of view, and resolution. Basically, a short focal length gives you a really wide angle of view. That means the car can see a huge, wide stretch of the street, which sounds great, right? But there's a huge catch. When you widen that view, the objects inside it, like another car or a pedestrian, end up taking up way fewer pixels. They literally look smaller and become so much harder to define. So you're stuck. If you want your car to see a super wide area to catch, say, a pedestrian unexpectedly stepping off the curb, you end up sacrificing the high-resolution detail you desperately need to actually figure out what that object is. It is just an endless tightrope walk for hardware developers. Okay, so once that LiDAR hardware actually captures the environment, the raw data it gets back is basically just a chaotic blizzard of laser reflections. It's mostly noise, so it has to go through this incredibly strict processing pipeline. Step 1 is isolating the raw detection of solid objects, what the engineers actually call Type 1 detections. These are your cars, your pedestrians, things like that. The system has to aggressively filter out all the random noise, like electromagnetic interference, ground clutter, or even just bad weather. Then we move to Step 2, which involves grouping and clustering all those meaningful data points together. This is so the car can recognize that a specific cluster of pixels isn't just random, it's actually a single cohesive object. And finally, Step 3, target tracking. Because the car doesn't just need to know where an object is right now, it has to predict its motion. It needs to know exactly where that pedestrian is going to be in, say, 1.5 seconds. Now, the really crucial question is, how on earth does the autonomous brain make sense of all this clustered data in a world that is, let's face it, completely unpredictable? The magic answer here is unsupervised learning. See, the real world is just way too chaotic to pre-program every single possible scenario. You can't just hand the car an endless list of correct answers for every weird pothole, crazy weather condition, or unpredictable human driver it's ever going to run into. Instead, engineers use unsupervised learning algorithms. They feed the program massive amounts of complex data and basically tell it to optimize itself. The AI has to discover hidden patterns and relationships all on its own. Essentially, the car is teaching itself how to navigate the messy, gray areas of reality, making real-time interpretations without any human holding its hand. And, it's precisely in those messy, unprogrammed gray areas where our amazing technological marvel collides head-on with massive societal consequences. We've talked about the fancy algorithms, the lasers, the hardware trade-offs, but as these vehicles get closer and closer to widespread everyday deployment, we really need to zoom out. We're stepping out of the engineering lab now and trying to navigate a deeply complex ethical maze. Because deploying autonomous vehicles isn't just about making sure the car stays in its lane anymore. It is about managing the massive, real-world human impact of this technology. The source material for this explainer actually impartially outlines several really severe societal risks, and they prove pretty clearly that engineering perfection does not automatically mean ethical perfection. First up, there's algorithmic bias. If that unsupervised learning AI we talked about is trained on flawed data, it might start making decisions that unfairly disadvantage certain groups. For example, it could turn out to be less accurate at detecting pedestrians of different demographics, or maybe people using wheelchairs. Second, we've got to look at the very real economic shockwave of job displacement. Sure, autonomous trucks could brilliantly optimize our supply chains, but they also threaten to displace millions of human drivers. That's going to demand massive social safety nets and massive retraining efforts. And third, data privacy. Think about it. A fully connected autonomous vehicle is essentially a giant roaming data vacuum. It's collecting incredibly detailed information on a passenger's exact locations, their habits, their daily routines, which creates unprecedented vulnerabilities to hacking and mass surveillance. So, to manage all these massive risks, the industry desperately needs a moral compass. Policymakers and manufacturers have to find a way to balance this rapid innovation with a really essential framework of strict safety protocols. The dues here are pretty clear. They demand prioritizing absolute transparency in how an AI actually makes its decisions and investing heavily in data security. It also means we need to bring diverse stakeholders to the table. We're talking ethicists, the general public, city planners, not just tech folks. And the don'ts are just as critical. Companies absolutely cannot afford to ignore public concerns. They can't just rely on an echo chamber of their own internal engineering teams, and they definitely cannot cut corners just to be the first one to get their shiny new product to market. Unchecked ambition in this space literally has life-altering consequences. Which brings us right back to exactly where we started. No matter how advanced that 3D LiDAR becomes or how incredibly sophisticated those unsupervised learning algorithms get, failures are going to happen. The impossible crash scenario will eventually present itself out there in the real world. And when the dust finally settles on that unavoidable collision, society is going to have to answer one final profound question. Who is truly accountable? Is it the manufacturer who physically built the car? Is it the programmer who sat in a lab and wrote the unsupervised learning algorithm? Or is it the quote-unquote user sitting in the driver's seat completely detached from the steering wheel? The technology to take our hands off the wheel is practically already here, but the responsibility of figuring out what happens next, well, that rests entirely on us. Thanks so much for joining me for this explainer, and I really hope this leaves you with plenty to think about the next time you see a self-driving car out on the road.